What is sigma notation? Well, first of all, sigma is a Greek letter, just like pi or theta. This is the capital sigma, which is what we're going to be talking about. The lowercase sigma looks like this. It's used for things like standard deviation. Um, but this capital sigma stands for summation, and frequently people will say the sum of a large thing. So uh, this is an abbreviation for that expression. So we read this: the sum starting from m through n of a sub I. So what this means is we're taking I as our index of summation. I'll write that out: index of summation. And we're going to change I between the value of m and n. So we're going to start with I equal to m. So this is the first term. When I is m, then we have am. Then we go to the next number above it. So after m, we have m plus 1. So now we find out what a sub m plus 1 is. Then a sub m plus 2, a sub m plus 3, a sub m plus 4, and we keep going until we get to this. So this m here is the lower bound of the summation, and this is the upper bound. Typically, you'll see sums where it'll look like this: I equals 1 up through 3 of, say, I cubed. And this is saying plug in 1 first, then plug in 2, then plug in 3, and now we've plugged in 1, we've plugged in 2, and we've plugged in 3. So that's all the numbers between, all the positive whole numbers between 1 and 3. And we'll write it like that. So it's the summation from m to n of a sub I, or the partial sum of a sub I from m to n. Now it is possible for this to not be a partial sum. If you see something like this, then that's going to be an infinite sum, where this would be like, say, add all the numbers 1 plus 2 plus 3. And under normal techniques, we'll say that that's infinity and it diverges. But typically, we're gonna start dealing with partial sums with a number on the top. So to evaluate arbitrary partial sums, meaning we don't have to know anything special about the terms being added. First, you identify how many terms are being summed using the lower and upper limits of summation. Then evaluate each term in the sum by substitution, and then add those terms. So here, I'm going to use the 0 and the 4 to determine how many things there are. Now it's not 4 minus 0 gives you 4. It's 4 minus 0 plus 1 gives you 5. There are 5 things that we're going to be adding together. 1 when it's 0, 1 when it's 1, 1 when I is 2, 1 when I is 3, and 1 when I is 4. So I is 0, 1, 2, 3, 4, because the index is from 0 to 4. Now we'll plug in, by substitution, 0 squared minus 2. We have 1 squared minus 2. The absolute value of 2 squared minus 2. The absolute value of 3 squared minus 2. And the absolute value of 4 squared minus 2. So now we evaluate each of these separately. So 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. Then we have 2. 1 minus 2 is negative 1. Absolute value is positive 1. 4 minus 2 is 2. 9 minus 2 is 7. 16 minus 2 is 14. And now we add these up. So that will give us 2 plus 1 is 3, plus 2 is 5, plus 7 is 12, plus 14 is 26, I believe. Yeah, that looks good. So this is the sum when we plug in 0, 1, 2, 3, and 4 into this expression. This is an abbreviation. It's not really necessary in this case, although you could argue that this is a lot to write. It's going to be really useful when we're adding this from 0 to 100. So let's do a little bit more practice with this. This is the same thing as, well, we're adding from 1 to 5, so that's 1, 2, 3, 4, 5 terms that we're adding. 2k plus 1, 2 times 1 plus 1. 2 times 2 plus 1. 2 times 3 plus 1. 2 times 4 plus 1. And 2 times 5 plus 1. You'll know one thing that people forget is what this number is. Ignore that. It does make a difference. This one started at 0. This one started at 1. Both of them have 5 terms because this is 1, 2, 3, 4, 5. This was 0, 1, 2, 3, 4. Now we evaluate these. 3 plus 5 plus 7 plus 9 plus 11. So you'll notice this is odd numbers. Please remember that 2k plus 1 represents odd numbers. And we're adding these odd numbers. We're adding 5 odd numbers. We are going to get 35 when we add those odd numbers. Well, we have j is 3, j is 4, j is 5, j is 6. Again, if you want to know how many there are, it's 6 minus 3, and we're always adding 1. The 6 is from here, the 3 is from here, and the 1 is always part of determining how many terms there are. So, we're adding 1 over 3, 1 over 4, 1 over 5, and 1 over 6. So, we're going to need a common denominator. The common denominator that works here is 60. This will be 20 sixtieths plus 15 sixtieths plus 12 sixtieths plus 10 sixtieths, which gives us a total of 57 sixtieths. We can simplify that, I believe. Yes, that is the same thing as, they're both divided by 3, so how many 20ths is it? 19 20ths. And this is kind of a trick in some sense. This is a really easy sum to evaluate once you're comfortable with what it means. This is from 0 to 500, so there are going to be 501 terms. 500 minus 0 plus 1. There are going to be 501 terms added here. And all of those terms are going to be 3. You'll notice I doesn't appear anywhere here. We had our index of summation appear in these. But this one, it's just 3. So we're adding 501 copies of 3. So we're adding 501 copies of 3. That's the same thing as 501 times 3. So the sum here is 1503. Lastly, how would we write the sum of the first 100 positive even integers using sigma notation? So positive even integers. Well, what do we write to represent an even integer? An even integer is always 2 times some other integer. So I'm going to write it as 2n. The first one will be 2, so that's when n is 1. And we want to add them all up between n is 1 and n is 100. So then the way we want to write that is from n going from 1 to 100 of 2n. This is how we write the sum of the first 100 positive even numbers.